First, I'd like to thank Daniel and Björn for organizing the session and inviting me to talk in the session. I'm talking about very recent research with my PhD student Santeri Karppinen. And what is this about? It's about hidden Markov model smoothing. So what's a hidden Markov model? It's a model that consists of two processes, so to speak. First, a latent Markov process X, okay, governed by known initial density M1 and transition densities M2, M3, M4, so forth. And a sequence of observations that are conditionally independent observations of each state with densities G1, G2, G3, so forth. Okay? And the smoothing problem is that we want to make inferences or look at the conditional distribution of the latent state given all the observations. And the diffuse initialization corresponds to the case where M1 is uninformative about the conditional law of X1 given the observations. Okay. And where this kind of a model could be useful, this is an example which is rather timely. I think many of us has been doing something like this recently, or at least looking at this kind of pictures. So this is just an attempt to estimate the basic reproduction number of an epidemic, or equivalent to the transmission rate of an epidemic, given daily observations of the cases. Okay? And well, this could be seen as a smoothing problem. Let's focus on the conditional particle filter then. What is that algorithm? So that algorithm works for the hidden Markov model, but we simplify it a little bit. So in fact, once we fix the sequence of observations, we can sort of fix these potential functions gk, which are just these functions evaluated at the different points xk. Okay? And then the smoothing density becomes just the law of the Markov process, the joint law of the Markov process, okay, modulated or weighted by these potential functions g. So in fact, this could sort of be in principle solved by importance sampling, by basically drawing samples from the Markov process M and doing weighting according to G. But simple importance sampling doesn't work quite well here because of the typical high dimensionality, which I will come back to later. But instead, what you can do is that you can sort of do something like importance sampling and construct Markov transitions that are rather efficient. Okay. And that's the conditional particle filter presented 10 years ago in that paper. And you start from a certain initial guess or reference state or reference trajectory in red here. You construct a number of particles at each time instant around the reference, okay? And then you choose a new state among all the particles, including the reference and the new particles. And this will be a valid pi-t invariant MCMC transition, okay? So instead of looking at the algorithm in pseudocode, let's look at the algorithm in picture. So here, imagine that the GKs are just functions that are concentrated around the yellow point. So they are essentially zero very far from the yellow points, and they have high values near where the yellow points are. And this is the reference trajectory here. And the M's here are following an AR1 process, which is like random walk kind of behavior here. like the reference has. Okay. So what we do here is that we build this, we sample these particles around the red point. So what happens here? We draw the initial samples from the initial density M1, and then what we do is that we select n times among from these particles and then augment those initial state with the second stage using M2. And the selection is done by the weight G1 here. And we repeat the process for on and on and on. And because of this sampling and weighting and selection, you end up having this kind of a tree-like structure in the algorithm. And then what we do in the final step of the algorithm is that we choose a new state. So how do you do that? You pick one of these last time instant points or particles, and then you follow the gray lines up until the beginning. Okay, and it looks like this in the example case. Because we can select from the reference trajectory, this is often what happens, is that the blue and the red actually are having the same trajectory or sharing some part of the trajectory. Here we have been rather lucky with the third iteration and almost moved the whole trajectory. But in fact, well, the algorithm doesn't look so good because the Markov transition from red to blue doesn't seem to move so much. But this just means that we have too few particles for this length of the time series. We should have more particles, okay. But instead of adding particles, we can do also something else, which is introduce backward sampling step. So this is an easy algorithmic modification of the conditional particle filter. And intuitively, you can sort of describe it just as forgetting the gray lines and drawing the gray lines again from their conditional distribution. Okay. So it is still a pi-invariant Markov transition, but it can be much better. Let's look at the picture. We still have a reference where we start from. We still do the tree-like structure of the particles around the reference as before. The difference is now that instead of drawing one of the states here and following the gray lines up until the beginning, we don't follow the gray lines, but we actually sample each step backward. So we can choose any one of the particles, any one of the gray points at any time instant. And this often leads to blue trajectory being quite dissimilar from the red trajectory. So you see that, so you can imagine that this actually mixes much better. And indeed, at least we know that it cannot mix worse than without the backward sampling, okay? But then, interestingly also, for long time series, both of the CPF and CBPF, under certain conditions, behave rather well. The difference, sort of roughly speaking, is that for the CPF, you do need to increase the number of particles linearly as a function of the length of the time series, okay? Whereas you can apply the backward sampling variant with constant number of particles, okay? But what was the problem we were interested in? It was diffuse initial distribution. So before, in that example, we didn't have diffuse initial distribution, but actually the initial distribution was rather well located around the smoothing distribution, okay? But let's look what happens when we have more diffuse case. So here, it's exactly the same picture, and the only thing that has changed is the initial distribution here. And the initial distribution is now a really big, wide normal distribution. And in fact here, there are only two particles visible because all the rest of the particles fall outside this window. But actually, even in this case we were lucky, and in the first iteration we're doing quite well. But if you iterate, you often end up in this kind of a situation where you don't move the initial point at all, because there are no good candidates at the first time instant. Because the first time instant particles were drawn from the M1. If M1 is really diffuse, most of the particles are wasted, and you end up being something like this. Okay. So this is the problem we are trying to solve here. Okay. And now let's focus on the algorithm just with one time step. So let's forget about all the rest of the trajectory, and let's look at the algorithm only with one time step. So what happens? It's simple enough algorithm in this case so that we can actually look at the pseudocode and the details. So now the target is just the product of the density m times potential g. I've dropped the time indices 1 here for simplicity. Okay. And what's the algorithm? It's the reference, red x star reference, so that will be the particle number 1, okay? And the particles 2 to n are drawn independently from m. Then we calculate the weights, which are just the potential value at the point x, normalized so that the weights sum to 1, okay? Then we draw one random variable, an index proportional to the weights, and pick that particle to be the output. So if it happened to be b equals 1, then we draw the red point. If it's not, then we draw then we picked one of the other particles and moved. Okay. So you can regard this as a multiple try metropolis, but indeed a multiple try independent sampler, because we are proposing from an independent proposal n. This defines a pi reversible Markov transition, okay, rather easy to see, and it's valid with any number of particles. So n is just a tuning parameter, but it's valid with any n. But if you look at the situation, what happens with large n is that nearly always you accept or you pick one of the other particles, not the reference, okay? Because the weights are sort of order 1 over n because of the normalization. Okay. But we don't care about the asymptotic n being very, very large, because we want to implement this algorithm with reasonably small n. So the algorithm generally works rather well when m is close to pi. So if g is sort of roughly constant or takes typically quite large values when we draw from m, then this algorithm is good, because then small number of particles, say 64 or 32, is enough to give you a very good accept rate. But if g is really peaked, so if we draw from m we rarely hit the peak of g, then we often end up keeping this red guy and need an astronomical number of particles n to actually make it mix well. Okay. And the thing is that, of course, we can sort of imagine that we could tune m and change the g so that we keep the same pi, but the independent sampler is known to be hard to tune in practice, but random walk moves might be actually better. So let's try that. So if we just blindly sort of try to implement the algorithm so that we change drawing from the independent proposal m to draw from a dependent proposal here. Let's think about the case where m is just 1 and q is simply a random walk move. Let's try this. Okay, so is this a good algorithm? Well, the answer is no, it's not. It is not pi invariant anymore. So this will be a biased algorithm, and not so interesting. So is it hopeless to try to do anything like random walk here, or is it really complicated? Well, it turns out that it's not. We need only a little modification of the previous algorithm to actually make it work. So we still have the same situation. We are at the current reference point, red point here on the plane, and this is our proposal here. But instead of drawing all the particles from this proposal as we sort of attempted before, let's pick just one particle or one green point out of this proposal distribution. And then let's forget about the red point entirely for a while, okay? And let's focus on the green point. So let's place our random walk proposal around the green point now. And let's draw all the particles around the green point, okay? And now just completely ignore the green point and just proceed as in the CPF. So select from the gray or the red one according to the weights as before, okay? And this turns out to be a valid algorithm. If we did this one step here where we draw an auxiliary center for the proposal from the same proposal, and then the particles from that works. The only thing we actually need here is that this transition Q is M reversible, okay? In general, it works. So in our example, M was uniform, okay, so that's constant, but Q was just symmetric, random walk, okay? But we can, for instance, look at the standard CPF case by plugging in Q to be just an independent draw from M, okay? And the reversibility is satisfied, again, trivially. But actually in this case, the step one is redundant. We can just drop it. Okay, so how does it look like when we have more than one time instant now? Okay, is the algorithm more complicated? Well, of course it is, but not so much. So the reference is here, okay, as before. What we do now is that we draw from Q that leaves the M1 invariant, okay, an auxiliary point, and then we draw from the same Q all the particles for the first time instant. But after this point, so this is sort of this three-step or two-step procedure replaces drawing from M1 in the conditional particle filter, but the rest of the conditional particle filter is the same. And we can also do the selection either with or without backward sampling as before. Here it's with backward sampling. Okay, and of course then you can ask for, there are two special cases that I noticed there. The random walk, so typically you might be using a Gaussian random walk. This is what we were considering, okay? In some cases you do have a uniform uninformative initial distribution, but you do have some domain, some constraints to fulfill with the initial state. Then you can modify the symmetric random walk just by including rejection. If you draw a state that falls outside the domain, you actually don't move at all, or the point will be the previous reference, okay, of the previous point. And then in the normal case, we could use an autoregressive Crank-Nicholson type proposal. And indeed, if M1 is proper probability distribution, we can apply any M1 reversible MCMC transition. And we can really do this because we only need to be able to simulate from Q, no any density values or anything like that. These proposals are rather general, but they do have tuning parameters. So in the random walk case, we would have a proposal covariance, and in the Crank-Nicholson type case, an autoregressive parameter. So let's think about the covariance. So you can imagine that is going to be important, that you choose the proposal covariance well, like in the random walk metropolis. So we choose to adapt they so choose it automatically during the simulation. So what we do is that we adapt the shape and a scaling factor of this proposal covariance at every iteration, so that eventually the shape matches the covariance of the first marginal of the smoothing distribution. Okay, and then we also match the scaling factor or tune the scaling factor so that we get a certain desired acceptance rate in the end. And acceptance means in this case that the initial states are different. And we noticed that about this range of values often seems to result in a reasonably good mixing chain. In many cases in practice we don't just care about smoothing, but we care about the situation where we actually have M's and G's, or the hidden Markov model, indexed by unknown hyperparameters theta. And in this case you can use another particle Markov chain Monte Carlo algorithm, that is the particle Gibbs. The particle Gibbs is nothing more than alternation between the conditional particle filter and then a standard Gibbs or metropolis within Gibbs moves for the parameters. Okay? The nice thing about this is that actually here we have the conditional particle filter, so that's in the original particle Gibbs. What we can do is that we can just replace that with the auxiliary initialization algorithm directly. And that's the only thing we need. We only need to be able to have n1 theta reversible q theta. But in fact, in practice, if n1 is diffuse, most of the cases it doesn't depend on the parameter at all, so we only need one q. And here is an application or a test of this method. Does it really help at all in the epidemic example? So this is our algorithm. So it's the particle Gibbs using the auxiliary initialization CPF, okay, and including adaptation. And it actually produces trace plots that look rather good, well mixing Markov chain. And this is an alternative which we can implement rather easily. It's that we take the initial state of the latent process as a parameter in the particle Gibbs. So we sort of do parameter augmentation, and we can run the particle Gibbs like that, okay, including also adaptation. And it also works, but it is just not so well mixing than our approach. Okay, so there is some earlier related work. So in case t equals 1, at least the random walk version of the t equals 1 case that I showed, that has been suggested before. And then the AICPF does fit the general augmentation scheme presented earlier as well. But in fact, if we use the AICPF within particle Gibbs, I did think it doesn't fit this augmentation scheme anymore. But anyway, I think our focus is rather different. So our focus is on M1 reversibility. It's rather general though, and this could be a useful approach in other contexts than diffuse initialization as well. And just as a take-home message, I think this is an easy modification of the conditional particle filter if you have diffuse initializations. So you can just replace your standard conditional particle filter in the particle Gibbs by plugging in the auxiliary initialization method. You can get substantial improvement with sort of little cost in terms of implementation effort. And adaptation, that can really be nice because you don't have to be doing a lot of tuning, but instead you can just plug it in and let it adapt, and it seems to work rather well, just like that. And here are some key references, and this is the paper, and that's the link to the code. Okay, thank you.